Welcome to the short recorded lecture on continuity. This is very abstract in terms of being the continuity of a function f, a mapping between one metric space and another, not necessarily the reals. So the definition given in the book and the text that we're using is the one that I prefer very strongly, and it's the sequential perspective. This is sometimes also called sequential continuity. The idea being that a function is continuous if for every convergent sequence Pn in the metric space M that you can consider, the output sequence f of Pn in the metric space N converges to f of P. Now notice he is using, the author Pugh, this notation fp to be f of P. He says it is a convenient shorthand. I think he is lazy at typing because it is not that much work to write of P and it adds a great deal of clarity. I think this looks like a typo. So I do not like that, and so you will not see me using that. I will use this notation here for function, and he's not even consistent using that notation here. So yeah, we'll just move on from there. But this is a great definition because the proofs are let Pn be a sequence in M that converges to a point P, and then you need to show that f of Pn converges to f of P in this new metric space N. So the proofs are pretty short. They're very direct. It's a very forward perspective. This is what I say at the bottom of this page, so you should read it. The idea is that a limit passes through a function. So the limit of the function values on xn, so this is existing in that metric, the new metric space right there. The limit of the function values is the function of the limit. So that's what I'm showing in symbols here, is that the limit passes through the function. So that's a nice way to think about continuity. There's also an epsilon delta criteria for continuity that is completely equivalent to what we have to the sequential perspective on continuity. It's very similar to what you've seen in elementary analysis. You have your, for every epsilon greater than 0 and every point in the metric space, there's then a delta, such that if you take the points in the input space M and you control them, so delta is like a control that you impose on the points x so that they do not exceed a distance of that control delta from P, then the output values are within effectively the error tolerance defined by epsilon. This is a nice conceptual way to think about continuity if you're considering what it means for a process to be continuous. And while you can also think of it as it's equivalent to thinking of passing the limits through it, it's nice to think of epsilon as an error tolerance, and that a continuous process means you're able to control the inputs of the process in order for your outputs to be within some desired error tolerance of some ideal goal target value, f of P. So these two are completely equivalent. I sketch out the basic proof that you've probably seen from the elementary analysis about the equivalence of these, especially if you go look in the Ross book I recommend. The only thing that really changes is the notation. So I recommend, I just kind of wrote all out, this is more of an outline of a proof, but it's a fairly detailed outline, but you should try to turn it into a top-down proof using the book's notation, maybe not his f of P, but m's and n's. It's a good translation exercise. Although I'm not a big fan of his notation because n for a metric space kind of removes the ability to use n as an index. And these could all these inequalities can be less, greater than or equal right there in terms of the indices. So this is just an outline. It's to get you started. It's based on old notes that I typed up. So it's up to you if you want to go and do it, but I highly recommend that students turn this into a top-down proof. And also that you ask yourself why we must use contradiction for one of the directions of this if and only if proof, that the epsilon delta criteria for continuity and the sequential definition of continuity are equivalent. So then an example, the first example I give you is I let C superscript 1 here denote the space of continuously differentiable functions on a closed bounded interval, meaning that they're differentiable on the open interval, but that they can be continuously extended on the closed interval. So that's what I'm meaning by this space. And notice for this metric, I'm using d sub 1 of fg to be the sup norm distance between f and g, and the sup norm distance between their derivatives. So with that metric, with this metric d1, the operator capital D that's defined by differentiation in the usual sense that d of f is f prime, where you're equipped with the uniform metric d0, just meaning this part right here, that this operator d is continuous. And I give you a sense of there's a lot of notation here. You might want to create a table. This table is very useful to map things from the definition of continuity, like what's your input space, what's your output space, what's a point in the input space, the function f, and output values y. These are for kind of the abstract definition using x and y instead of m and n for the notation for the input and output metric spaces. And then think, well, what are the corresponding terms in this specific problem? That's showing up on the right-hand side of this. And so, right, our input space is the continuously differentiable functions with d1. There's a little typo here. That should be a d0, so you should fix that. That's our output space. And then we have this, f is really a point x in this problem here because we're talking about a function. And then the mapping between the two spaces, instead of thinking f as a mapping from x to y, the mapping in this case is given by capital D, meaning the derivative. And this is what outputs look like, f prime. So good idea to do that if it seems like a lot of notation, and especially when you're solving these problems with very specific metric spaces that are not the reals. Not a bad idea to make a table for yourself like this, just so you can map all the notation of that problem onto the definition that you're using to prove continuity. Now, the proof is not too hard. Like I said, there's 2 steps with sequential. You let Fn converge to F in C1. So you can write this even more simply, and I start doing that at some other points. You could just replace this with let Fn converge to F in C1 of AB. This is a fine substitution for that. That's okay. If you want to do that, that's great. If you're not, you can be a little bit more verbose, but I'm kind of giving you like the maximum verbosity that you should use, which is shown here. Don't write more than that. And you can write even less, as I'll show. So you consider this convergence sequence in the input space, and then what I need to show is this at the end. That's it. I need to show d of Fn converges to d of f. And what I'm doing is using a result from a previous lecture note, one of the results that says that convergence in a metric space is equivalent to showing that the sequence of real numbers defined by the distance between the things in the sequence goes to 0. So I'm using that result to say that's equivalent to showing this convergence. So I've outlined the details here. This is all I believe already provided in your lecture notes. You should try an epsilon delta proof. Something that I missed on the notes that I gave you was to say that prove that t is continuous for this map here. So now we're having the space of continuous function C, metric space of continuous functions on AB. The metric I'm applying on that space of points of functions, of continuous functions, is the integral metric. And then I'm taking the integral of a function, right, which turns it into a real number. So this is a mapping from a space of continuous functions into the reals. And I ask you to prove that t is continuous. Again, it's pretty straightforward. There's 2 steps. Step 1, here I let Fn converge to f in the space of continuous functions. It is assumed when you write that based on the way the problem is stated, that the metric that you're talking about is from the description of the problem. So it's with this metric. That's what we mean when we say it converges in this space. It means with respect to them using the metric that was prescribed on that space, which in this case is given by the integral metric. Then step 2, I need to show what? I need to show that t of Fn converges to t of f. And again, this is made quite straightforward by using the equivalence that the output space is the reals, and the convergence in the metric space just means I have to show d of 0, d of r, t of Fn, t of f converges to 0. All right. So that's all I'm doing here, and I'm just going straight to I know what that metric is, the metric on the reals. If there's no metric specified on the reals, you're using the usual metric on the reals, the absolute value of the difference between 2 numbers. So I just go through that here. I spell out more of a specific reason about how I got to this step right here, which involved the linearity of an integral, which is, you could also just write that as an elementary analysis result. So you could just write EA right there. That's fine. That would be okay. And by another elementary analysis result, that the absolute value of an integral is less than or equal to the integral of the absolute value. I then get that this is actually going to 0 because that is this, right? D of, that is the metric. This is going to 0 because, so if you wanted to know why, how do you go from here to here? It's because D of Fn, F, goes to 0 because you said Fn converges to F, right? So I'm just using that result, so I'll clean this up. I also provided an epsilon delta proof here just so you see the details. To show continuity on a set, you have to consider, this is kind of like an optional thing, but you have to consider an arbitrary object, an arbitrary point in that space, and the arbitrary epsilon greater than 0. So you do always have to at least talk about epsilon greater than 0, but if you're not proving continuity at a specific point, you have to let yourself consider any point in that set. Because the delta that you might pick could depend on both the epsilon and the f. In this case, it only depends on the epsilon because this is actually a uniformly continuous function. And then you have to consider any arbitrary point in the space that's within a delta distance of that specific point that you have up here. And then you have to go through the whole rigmarole again, which is very similar to what you have to do to show the convergence of sequences. And that's what this last step is. So the epsilon delta has proofs have more steps. Again, highly recommend just doing the sequential and getting used to that. Okay, erase those parts. Then with this problem, I should have said, I think it was implied, but I should have said that the sets A were non-empty. The idea here being that the distance from a point in a metric space to a non-empty set A is defined by taking the infimum of the distance from x to y over all points y in that set. All right, that's how we define that distance. So for a given non-empty, for a fixed non-empty set A, this defines a function that maps points in x to real numbers. Again, with the usual metric on R. And I ask you to show that this is continuous. So I'll kind of just leave this up here. You can pause and fill it in. I wanted to point out, though, the use of a few things. I was very, very detailed in writing out the justification of a lot of steps here. But I did just say that this is elementary analysis to get to this inequality. And it's very much related to results involving supremums and proving that the sup norm is a metric in some cases that we've seen early on that students have asked about and posted proofs and asked for feedback. So if you're not sure what elementary analysis results are getting me from this step right here down to this next step, then you should go review those involving supremums and see how I'm using them how I basically am using similar results with infimums here. And then I use the definition of infimum to just remove it so that I can put in a fixed but arbitrary point from the set. That way I can exploit symmetry to get something in the form, so I can use the reverse triangle inequality, which I said was very useful inequality, I believe, in Lecture 2, the last page of Lecture 2. So I go through all of that to show that f of x converges to f of xn. So as soon as you show that the distance in the metric space, the output metric space, is between f of x and f of xn is going to 0, you're done. That's equivalent to showing convergence, based again on a problem from the Lecture 3 or Lecture 4 notes. And then there's some other results here that I won't read to you. I just suggest that students write down top-down proofs. I think there's enough details on this for students to work through. And this page as well, I think, has a nice set of results for students to look through. This last problem is actually quite interesting. It might seem a little strange at first, so I'm going to highlight something here for you. Let's change this. We're generalizing the definition of continuity to say if a sequence converges in the metric space M, then the sequence f of Pn has to converge in N. And you can say, how is that any different than the definition of convergent or continuity? How is this a different definition of continuity than the original one? So I described building a strategy for how to prove this, just describing like what are we proving, how do we prove it, but there's this issue here. It's really pointed out in step 3 of building a strategy to solve this. Is if Pn converges, you're saying, well, that means it converges to P, right? And you should be able to prove that limits are unique. If you haven't done that yet, you should realize that. Well, Pn converges to P. And the way this problem is stated for the idea that this is an equivalent notion of continuity is, well, f of Pn is now known to converge. But this problem is not saying that it converges to f of p. It's just saying that it converges. So what you need to figure out is, how do you actually prove that what it converges to is f of p? And I give you an idea here, and it involves the mixing of sequences related to something in your homework. So if you haven't looked at the homework problem, the homework assignment involving sequences, assignment 2, I believe, you should look at that now. And then you should consider how I'm suggesting you exploit that result to prove this one right here. So with that, I will end this video. Thank you for listening, and I'll be talking to you in Lecture 6.